Sure. Usually I don't really look at the clock or something, so it would help to like maybe, I don't know,
5 minutes left.
Hmm? Yeah.
Right, so like 45.
Yeah. I have yeah, 5 or 10. I don't know what's useful. Usually have you guys been doing 10-5?
We haven't been doing anything, so
Oh,
I
okay.
will ask, but I personally find it useful to know.
Yeah. Yeah. I'm not worried about going over time.
Yeah, I'll just give you, I'll give you a 5 minute.
Sounds good.
To apply this. All right, good afternoon, everybody. We'll get started now. Okay, I'm very happy to introduce our next speaker, Mikhail Solon, who's a professor here at UCLA. He's actually a relatively new member. He joined our faculty in 2020. Prior to that, he pursued his PhD from Chicago in 2014, and then he was a postdoc at Berkeley and Caltech before joining us. And as you've already heard, he recently was awarded a Sloan Fellowship, so we're very happy about that. And so Mikhail is an expert in use of effective field theory, which is a tool that works in a vast range of physical phenomena. So he'll be talking about one application of that today, which is gravitational waves. And so his title is From Elementary Particles to Binary Black Holes. Mikhail.
Thanks. You guys can hear me? Is the volume good? Okay, cool. Yeah, thanks so much for this wonderful event. Thanks again to the organizers. Manny, happy birthday and congratulations on what you achieved. And thanks for giving us a very good reason to celebrate and be among friends. So yeah, my title is From elementary particles to binary black holes. And today I want to tell you about, well, if the clicker worked there. So maybe I should just stick to this. So I'm going to tell you about a universal tool that we use in theoretical physics that's been remarkably successful and really describes every experiment that we've done. Okay, so it describes, for example, the elementary interactions of particles that we've seen at colliders. It describes, for example, the statistics of many body systems that are undergoing transitions, phase transitions. And facets of it have been used to describe, for example, the evolution of the universe from the quantum fluctuations at the beginning all the way out to the galaxies that we see today. Not only is it successful in describing things that we've made measurements on, it also gives us a very good framework to think about new questions. There's a lot we don't know. We don't know what dark matter is. We don't know a lot about the nature of the quantum fluctuations at the early universe. And we don't know how to do quantum mechanical calculations at the horizon of a black hole or inside a black hole. But many of these questions, actually, this tool gives us a very rigid framework to think about it. And not only think about it, but perhaps someday really probe its nature through experiments. And this tool is called quantum field theory. And from what I've said to you so far, you might think that it's such a powerful tool that you could think of it like Google Maps or Waze if you're trying to navigate the LA traffic. But that's not quite the case. In fact, a lot of the roads that you follow when you are thinking about quantum field theory actually lead to nowhere, lead to these uncharted territories or wild spaces where the textbooks end. And you're left on your own senses to make sense of things. And this sense of adventure, I think, is at the core of the founding of the Institute, and its research endeavors today. The idea of trying to understand deep properties of quantum field theory and at the same time apply it broadly to understand the nature of the universe that we live in. Okay, so how does quantum field theory work? In a nutshell, it has in it constraints, or it's a consistent framework where that has in it the properties of quantum mechanics and space-time. Okay, so the structure of space-time is built into quantum field theory. Now, I'd like to go through a few examples of this, concrete examples of the power of these ideas. So the first thing that we're going to do is we're going to try to discover Einstein's gravity without thinking about elevators, just using a simple calculation in quantum field theory. Next, we can use this theory of gravity to compute Newton's law and actually both classical and quantum corrections to Newton's law. And finally, I'll end the talk by talking about state-of-the-art applications of this for understanding binary black hole coalescence. So one of the remarkable things about the time that we live in now is that we can both hear or listen to black holes merging, and we can also look at pictures of black holes. So let me just start with the first thing. So we begin with a very elementary question, which is what type of long-range forces can there be? Okay. And in quantum field theory, the answer to this question comes from a very simple object, which is sometimes we call it the 4-point interaction or 4-point scattering amplitude. It basically is a mathematical object that describes for us the ways in which two particles, 1 and 2, let's see if this pointer works, 1 and 2, come in and come out as 4 and 3. So in this diagram, for example, 1 and 2 come in, they combine into a single particle, and then they come out as 4 and 3. In this other diagram, 1 and 2 come in, they exchange a particle, and then they come out as 4 and 3. In this diagram, 1 and 2 come in, they exchange a particle, and 3 deflects here, and 4 goes up there. Okay? And this is a process, a very simple process, one of the basic underlying building blocks of how we describe, for example, the dynamics that happen at collider physics. But it turns out to be really strongly constrained by the properties of QFT, namely that the fact that the space-time structure is built to it and the properties of quantum mechanics. In particular, we will be honing into one property, which is that poles in the mathematical function that describes this process have to come from propagating particles. Okay, they have to be interpreted as propagating particles. Sometimes this is called locality. Okay, so let's look at this in a little bit more detail. Suppose that all the particles 1, 2, 3, 4 are of a single type. And suppose that it has spin 1. So we're imagining we have particles of spin 1, a single spin 1 particle. Take 2 of them, they come in, they combine, they come out, and so on and so forth. Well, it turns out that if you have a single spin 1 particle, the poles are not interpretable as propagating particles. There are spurious poles. In other words, this function is non-local, and that's not something that, that's not a good property of the amplitude. So that's not allowed. And you might think, well, we know of spin 1 particles. Photons are spin 1 particles. So how come your calculation shows that photons can't exist? Well, this photon, as I said, all particles are the same. This photon happens to be interacting with itself. Sorry that the pointer, I think the pointer's not working. But as you see here, photon 1 is talking to photon 2 through that vertex right there. So photons, as we know, don't have self-interactions. Now suppose we tried spin 1 particles, plural particles. It turns out that in this case, there's actually a solution. So you can have a bunch of spin 1 particles. They come in, and then they come out. They scatter in all these 3 different types of ways. And there's a consistent solution where the poles can be interpreted as propagating particles. Okay? And not only that, we find that the vertices, or these interactions right here between these different spin 1 particles, are satisfy what's called the Jacobi identity, which is the hallmark of what's known as non-abelian gauge theories. Okay. More than that, if we took these spin 1 particles and asked how they coupled to matter, what we find is that they actually couple also in a constrained way in order to cancel poles. And that constrained way means that they must obey a Lie algebra. And so from this simple exercise of just looking at a 4-point interaction, the ways that these 4 particles can interact, looking at the properties of the mathematical function that describes this, we've just discovered that one possible long-range force is the Yang-Mills force, which is, for example, responsible for the strong interactions and also part of the weak force. Okay. Now suppose we said, okay, what about spin 2? If we assume a single spin 2 particle, just like we assume this single spin 1 particle here, in this case, it actually works out. Spin 2, a single spin 2 particle is allowed. In fact, again, if we look at how the single spin 2 particle couples to matter, it turns out that the coupling is universal. So it couples to matter the same way it couples to itself, and that is Einstein's equivalence principle. And so we've discovered gravity uniquely. This spin 2 particle is nothing but Einstein's gravity. If you go on, you can do the exercise further. You can, for example, assume a bunch of spin 2 particles. If you're wondering whether you could have some non-abelian version of spin 2, well, the answer is it won't work out. You could look at higher spin, higher than 2, and you won't find any solutions. So this simple exercise coming from a very basic object and quantum field theory that underlies a lot of the processes that we deal with in collider physics, for example, particle physics and so on, really gives us a unified picture of the fundamental forces. So we learn that the possible long-range forces are non-abelian gauge forces and gravity. Spin 1 particles are also possible, but you have to do a slightly different set of graphs where not all particles are the same type. You have to consider actually coupling the spin 1 to some charges. Cool. Thank you. Okay. Another remarkable thing about this 4-point function is it actually, after studying it even more, it actually reveals an even more unified picture of these forces. And this goes by the name of double copy, and this was mentioned several times during dinner last night. And it's called double copy because basically the fundamental force of gravity, which is that spin 2 particle, the mathematical function that describes this process can be written as that for the spin 1 Yang-Mills force, and then another copy of the spin 1 Yang-Mills force, hence the name double copy. Okay, so not only does this picture give us a unified framework to understand all the possible long-range forces, it also relates these long-range forces together. in fact, this relation extends to a web of theories where you can imagine a multiplication table where you take one theory, you stick it in here, you take another theory, stick it in here, and you get another one. Or you can, of course, consider a theory and peel off one of the factors and do division using this multiplication theory and get another one. And this interconnected web of theories includes all sorts of theories like nonlinear electrodynamics, but also some familiar ones like the theory that describes pions. Okay? Now, as I'll tell you later on, this has some powerful applications. If you're familiar with how complicated gravity is, this equation should excite you because this tells us that it can be, this complicated mess can be written as actually two copies of something simple. Okay, and that's where its power comes from when we apply it to the binary black hole problem. And finally, this structure has led people to ask whether this is a fundamental feature of these theories, what principle underlies it, whether it works in loops, whether it works for all sorts of other things. For example, people have even considered double copying not only amplitudes like these, but all order solutions. So solutions to the classical equations of motion that are not just a weak field. So here you have Schwarzschild solution of Einstein as a double copy of two Coulomb fields. Okay? So it's a fascinating subject. I won't say more about it, but I'll return to it a little bit when we talk about the application to binary black holes. Okay, so now that we have a theory for gravity, namely these spin-2 particles, what can we do with it? Well, we can check that it is indeed the theory of gravity that we know and love. And for example, we can check this tree-level diagram. We compute this amplitude. Now, in this amplitude, so previously I was computing amplitudes where all of the particles were of a spin 1 or spin 2 and so on. Here now I'm considering massive objects, so charge under the spin 2, exchanging a spin 2 particle. So this can be planet A, this can be planet B, and they're exchanging this long-range force that we just discovered. And if you do this amplitude and extract from it the force between these two particles, the effective force due to the exchange of the spin 2 particle, you find this equation, this familiar equation, which is just Newton's potential. So from amplitudes, we can extract Newton's potential. And if we consider at next order loop corrections, what we find, so here are some loop diagrams. So again, this is planet A, this is planet B. And you have now spin 2 particles interchange, but there can be a loop in here. So these are known as a loop of virtual particles. And there are a bunch of many ways of how these loops can be drawn. And I've only drawn 2, there are many more. But if you compute these loops, what you find is that there's this piece, the classical piece, and there's this piece where I've restored h bar. So particle physics like to use units where h bar equals to 1, but here I've restored it. And so you can see that this is indeed a quantum mechanical calculation. So this is Newton's potential, which was known in the 1600s. And this is the static piece of what's called the Einstein-Infeld-Hoffman potential, which was computed in the 1930s. And this is the quantum mechanical correction to it, okay? So quantum gravity is calculable, but unfortunately it is highly suppressed. If you plug in the numbers here for example, solar masses, then you find that this term is suppressed by something like 10 to the 78. Okay, so it's a really, well, sorry, 10 to the minus 78. So it's a really small effect. Nonetheless, it is calculable, and I only put quotes here to qualify it a bit. I mean, it is gravity. This is gravity. We're talking about gravity, and this is a quantum effect. I only put quotes here because this doesn't solve what most people talk about when they say quantum gravity. This doesn't, for example, give us a picture of what happens at the horizon or inside a black hole, but this is, a very clean calculation of quantum effects at long distances. Not only can we compute these quantum corrections, the rules of the game in quantum field theory tell us that if you have a degree of freedom, this spin 2 particle, then you write down all the possible ways it can interact with your other degrees of freedom. And the first term here is what gives Einstein's equation. So this is an action, and this term, if you vary it, you find Einstein's equation from this. But the rules of quantum field theory tells us that you can actually write down all the possible terms that obey your space-time symmetries and have your degrees of freedom. And in particular, you can write terms where you have three what's called Riemann tensors contracted, 4 of those contracted, and so on and so forth. And so not only is quantum field theory telling us that there is this long-range force, the spin 2 particle, which uniquely identifies Einstein's gravity, it also tells us that Einstein's gravity is not the complete theory, but rather generically we should expect corrections to it. Okay? This action where I've written S matter is just the action for these planets right here, which you can think of as point particles. Okay, and finally, just a quick comment. Might resonate with you if you've been taught in your courses or that loops are quantum effects. Well, as we can see here clearly, loops also contain classical physics, right? Okay, so the upshot is that these scattering amplitudes give us a unified view of the long-range forces. And if we look deeper into them, give us an even unified view in a way that these long-range forces are actually related to each other. And from them, we can actually compute the potentials that govern classical bodies, such as Newton's potential and corrections to it, okay? And in fact, it does so in a very natural way. You don't even have to fish out these classical terms from these amplitudes, because the correspondence principle tells you that in the limit of large charges, in particular here, I was thinking about masses of the size of the solar of a solar mass. You just compute those amplitudes, plug the numbers in, and you just get a natural enhancement of the classical term. So the correspondence principle says that in the limit of large charges, in this case, large masses and also large angular momenta, you just recover classical dynamics. This, by the way, is in contrast to the usual context in which we usually think of these kinds of calculations where we're dealing with, let's say, electrons or elementary particles where the charges are actually small in natural units. So for electrons, let's say you're thinking about QED, these classical terms that we've been talking about are actually smaller than quantum terms. So quantum terms are what's enhanced when you talk about electrons. Okay, so that means that we now have a framework for describing how 2 black holes orbit each other and eventually merge. We can compute, for example, higher loop corrections, not only just the static pieces that I showed you, but also the velocity corrections. So here, again, I have planet A, planet B, or black hole A, black hole B, and they're exchanging these spin 2 particles. And this would give us, for example, higher order terms in how these black holes, in how the black hole dynamics are described. We can also describe processes where one spin 2 particle is emitted out, and this is, for example, a radiative process where these 2 black holes are losing angular momentum and energy. We can also describe processes where these black holes have some internal structure. So these black holes are not really, let's say, black holes, but neutron stars where there's some finite size. And that finite size allows these bodies to squish or even spin. And in quantum field theory, we would describe these by adding higher dimensional operators. And we could even describe processes where there's more than one black hole. Let's say 3-body black holes that would be relevant, for example, for some of what Smadar described. Okay, and the really interesting thing here is not just that we have a framework, but this framework is really motivated by an ambitious experimental program that we heard from Barry. So we are headed towards an era where these 3rd generation telescopes will be online. As we heard, this crazy number of reaching Z equals 100, which I guess means that we can see every binary merger in the history, because I think stars formed before that. And that means something like 10 to the 6 mergers per year. And that's a crazy amount of data to think about. And hopefully there will be surprises for cosmology, astronomy, and particle physics. And so 3rd generation detectors will be very precise and give us this new view of the universe. But that means we need to do new calculations. Okay, so I'm not talking about taking Einstein's equation and doing new calculations from that, because the traditional approaches apparently are the bottleneck. Okay, so it's hard to do calculations that will enable the precision of these future telescopes. But this is where quantum field theory can come in. So the difficulties in these calculations are, of course, the fact that these are multiple scales that are nonlinearly coupled by general relativity. But exactly those two difficulties are what drove breakthroughs in quantum field theory in the past decades, leading to the ideas that I talked to you about, scattering amplitudes and effective field theory. And so we can use the same engines that are driving modern calculations in particle theory to understand the dynamics of binary black holes in a very precise way that will enable us to interpret or maximize the science at these third generation telescopes. So this is a cartoon of a calculation pipeline that my collaborators here at the Bombik Institute, as well as at Caltech, developed. And it starts, as the title of the talk suggests, with elementary particle scattering amplitude. So this is an amplitude in Yang-Mills. You square it using the double copy. So remember, we discovered that there is this unified view where you can take these different theories as factors and multiply them together and get other theories. So here, we want to take 2 copies of Yang-Mills and get a gravitational amplitude out. These gravitational amplitudes are then sewn using modern techniques in scattering amplitudes to a loop amplitude. These modern techniques were developed by people in this room, Lance, David, and Zvi. And from there, we use the whole machinery that's been developed for collider physics. So understanding of effective field theory, fishing out the relevant terms, all the way down to the bare bones integration methods. And from there, we get the classical amplitude. So these are the analogs of the amplitude that we looked at computing Newton's corrections. And then finally, we extract the potential that describes these binary black holes by essentially mapping this to a Schrodinger equation. And the potential of that Schrodinger equation is the potential that describes these binary black holes. Okay? And so this is a tremendous opportunity to really use these tools to make an impact on experiment. But at the same time, like I said, this is a new arena where you can play with quantum field theory. So we're used to thinking of small charges. We're used to thinking of amplitudes in that regime. But in this different regime where we're thinking about large charges, large angular momentum, different theoretical structures arise. And so this is an opportunity for us to learn something about quantum field theory itself. Some of these structures may be familiar from quantum field theory, but are not quite manifest or obvious from the point of view of binary black holes or traditional approaches to binary black holes. But at the same time, some of it might be just native to classical physics and is just not something that we think about in previous day-to-day use of quantum field theory. Okay. And by the way, this program was actually very welcomed by the general relativity community. So they themselves appreciate the power of these tools, and at the same time, appreciate the need for new ideas for computing waveforms for third generation detectors. Okay, and so here, for example, is a paper by a prominent general relativist, Thibaut Damour, and he clearly states, we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitude of scalar masses. So this would, for example, be a higher order correction to Newton's law. And broadly speaking, not only are general relativists interested in this for formal purposes, but they are really interested in this for using it inside the LIGO pipeline. So here are theorists based at AEI and Max Planck at AEI. And these are theorists at LIGO, Virgo, and Kagra, and they're definitely interested. They took the functions that we computed. So this is the tree-level function that I showed you, and the static piece of this gives Newton's law. This is the one-loop function that I showed you, and the static piece of this gives the function that I showed for Einstein, Infeld-Hoffman. This is the three-loop correction. Sorry, this is the two-loop correction, and this is the three-loop correction. And as you can see, plotting it order by order gets you closer to what here is taken as truth, which is this black dashed numerical relativity curve. And for comparison also, here is what's called EOB, or effective one-body. This is the phenomenological model that is currently used in these pipelines to describe waveforms. So these predictions, by the way, are computed by many people who are locally really here at Bomik Institute, but also many of the friends of Bomik Institute, such as Cliff Chung from Caltech. And the upshot here is that, these functions really do get the physics correct. It gets better and better, not quite as well as what they already have, but they're very interested in pushing it further because, again, they have this eye towards the future. And for example, one thing that they do is they actually reformulate EOB in order to naturally encode all the other new corrections that these functions have. And so in this formulation, for example, you can see that one of the functions, the 3-loop calculation does really, really well. Okay. Oh, I'm sorry. I didn't explain what this plot is. So the y-axis is the binding energy of two black holes. So we're describing two black holes orbiting each other towards merger, and this is the binding energy. And this is plotted as a function of orbits to merger. So here you have 20 orbits before they merge and so on and so forth. So as you can see here, the tree level calculation conks out at 20 orbits to merger. Well, 1 loop does a little bit better, 2 loop does a little bit better, and so on and so forth. So 3 loop gets you pretty close up to 4 orbits to merger. Okay. Another observable that they considered is the so-called scattering angle. So in the previous plot, we were thinking about two black holes orbiting each other, and there's a binding energy between them. They're bound. Here, they're not bound. This is following a hyperbolic trajectory where two black holes come in, and they go out, and there's a scattering angle that you can measure. And here are predictions, again, from quantum field theory. And as you can see, they, again, get better and better as you include more corrections. Here, again, is a comparison to what's considered as truth here is numerical relativity and the EOB framework. Okay, so the upshot really is that they find this extremely promising as a future tool, as a tool to make essentially the future happen, to enable precision at 3rd generation detectors. One thing I'd like to emphasize is that those results that I showed you is not just a recalculation of things, but really new results. So to show that, let me just plot here. Let me show you a map of the corrections to Newton's law as a function of Newton's constant g and velocity. So what's currently known via traditional methods in general relativity is in this blue triangle. This right here, this 1 is Newton's law. This right here is the function that I showed you, which was computed together with this function by Einstein, Infeld, and Hoffman. This is known as 1pn, for example, and 2pn, 3pn, 4pn, and so on. So this is the state of the art. What we need to really maximize the science at 3rd generation gravitational wave detectors would be something like 6pn, so 2 orders more than 4pn. So that includes up to g to the 7. Okay. And the calculations that I showed you on the previous plots are shown here in red. So this is all the information that it's encoded in there. So where the red box overlaps with this green triangle are checks, and we agree with these with these previous results. But everywhere else, these are new functions. And what's more interesting is that not only do you get new terms in this series, but rather you get whole functions, and these whole functions carry with them structure because you've carried around relativity instead of tossed it out. In particular, some of this structure due to relativity initially caused some strong doubts among the relativists. There were strong doubts of our results. In particular, there was papers written about alternative results for this number, for example, and so forth. And it had to do with this graph, which for the experts in the audience, you can think of as part of the Reggie trajectory of the graviton. And there's a log squared in here, and the log was bothering people. But in particle physics, we understand the source of this graph, of that log. We understand this graph very well, and eventually people were able to check the result, and now there's been multiple confirmations of this. At g to the 4th, currently there is also another puzzle that again has to do with relativity, and it has to do when some of these gravitons here are not quite what's called potential modes, but rather radiation modes. And in some cases, these radiation modes cause you to think that you could have certain effects called memory effects. but they're actually forbidden strongly by simple constraints such as Lorentz invariance and dimensional analysis. And currently there's agreement between our calculation and this group, but there's also other groups that currently do not have agreement with our result. And so again, just to emphasize that these techniques from quantum field theory are not just rechecking things, but really giving new perspectives on general relativity, but also the details of how binary black holes, of binary black hole dynamics. Okay, so what's next? One interesting thing that I think would be really good to tackle is just scattering in curved backgrounds. So I've been talking about spin 2 particles propagating in flat space, but there's a lot of information buried in curved background solutions to Einstein's equation. And if we can leverage those, then I think there's a lot of information that can be used for binary black hole dynamics. Consider, for example, again, the graphs that we talked about. So this one gave us Newton's potential. This one gave us Einstein infield Hoffman, and so on and so forth. Okay. In a curved space calculation, you not only get those first two, you actually get the whole thing. So you can actually resum this, and what happens is that the bottom matter particle is a probe particle, and the top source resums to a Schwarzschild background, and you get an amplitude that's all orders in G. Okay, and something that would be really interesting to figure out is how to do it with at the next order. So what's the next order? So if you stare at these diagrams, you'll notice that this is the class of diagrams where there's as many propagators on the top side as you want, but 0 propagators on the bottom side. So the next iteration of that would be 1 propagator on the bottom side and as many as you want on the top. Okay, and currently we know parts of this result, but not the full result. And why is that interesting? Well, it's an interesting field theory question on its own, I think, but also it relates to what's called the self-force expansion in general relativity. So these amplitudes depend on the masses of black hole 1 and black hole 2 in a simple way, just fixed by dimensional analysis. So the tree level amplitude depends on the masses as m1 squared, m2 squared. The one loop amplitude depends on the masses as m1 cubed, m2 cubed, plus the same term, but you just switch the labels 1 and 2, and so on and so forth. So the 0 SF result is this first column here and corresponds to the resummation of these graphs, where there's 0 propagators on one side and as many as you want on the top side. Okay, and so this describes for us a probe particle orbiting a Schwarzschild background. This next column here, where you basically, it's the one order down in an M1 over M2 goes to infinity expansion, is what's called as 1SF, and would correspond to the resummation of the graphs where there's exactly 1 propagator on one side and none, and as many as you want on the top. So it starts with 0 propagators on the top, 1, and so on, and up to 2 here, 2 here in my drawing, and so on and so forth. And this would be 1SF, okay? And like I said, we know parts of this result, but not the entire result. And for those of you interested, I can chat with you on what exactly we're finding and why it's not working out. And then you can continue to push, and this would be 2SF. And the reason this is important is because Lisa is actually sensitive to 2SF effects, but currently only 1SF effects are known. The 2SF problem has not been solved even numerically. And so it would be interesting to think about ways using quantum field theory to see if there's a solution that can be obtained. Okay, how many minutes do I have? Sorry, 15. Oh, okay. Well, it's my last slide. So let me conclude here. So I told you about how QFT gives us a new perspective on gravity. So we started by this simple example of a 4-point scattering amplitude, just asking of the different ways of how particle 1 and 2 can come in and 3 and 4 can come out. And we found a very unified picture that described the possible long-range forces. And among those long-range forces, we found uniquely gravity. Okay? And something interesting, of course, is that that's a perspective from QFT, but also Einstein's equations give us a different perspective. It's probably possible to think about some non-perturbative solutions coming from the QFT side, but Einstein's universe altogether with its exact solutions of Einstein's equation has given us these objects like black holes and cosmology and so forth. And it would be interesting to think, just like in my scattering amplitudes in the background question, of how we can leverage this side of the picture to learn more about how QFT works, for example. And I talked in some detail about the application of these ideas to binary black holes. In particular, we are really trying to leverage the tools that have been honed in collider physics, for example, even in G-2, to really understand binary black holes to high precision. And this has, I would say, the hallmarks of a great problem in theoretical physics because A, it's closely tied to a very exciting experimental frontier, namely the gravitational wave science program. B, you get to use quantum field theory, which is, again, the universal tool that we know and love. And finally, it offers us an opportunity to learn about theoretical structures in both of these important theories. Okay, finally, let me just say that it's a real privilege to have the freedom to explore quantum field theory, these wild spaces, these roads that lead to nowhere. And this is something that we really cherish here at the Bomic Institute. And so I just want to emphasize to you, Manny, that this is something that we really cherish and appreciate. So thanks. Yeah.
Thank you very much. Are there any questions?
It's rather interpretational part, but I would like to say that what you're considering, it's not quantum loops. It's iteration in external current. So you can say there's a classical equation and you're solving a nonlinear equation in higher orders, right? I mean, technically, it's nothing against what you're doing, right? But I'm trying to differentiate it from, kind of a full loop, because then gravity is still non-normalizable theory, and if you're talking about loops in quantum sense. So this particular part, which is associated with this long range, whatever iteration of external current, I would still call it classical. I mean, and you said it is classical, but I'm trying to say that the word loop is a little bit kind of make that kind of misleading, like that it's a real quantum correction. But I think that in this way it's still classical.
Well, part of it is classical, but why would you say that the other part is quantum?
No, because when you're saying this.
Yeah, so I think I understand your words, and I think that corresponds to the piece that I labeled as classical.
Right, you can say that this. Yeah, closer. Mm-hmm. Yeah. Okay, thank you. When you're writing loop, then you see that this just write a classical equation. Then it says that you're iterating over
That's right.
currents, right?
That's right.
Then I would call it classical solution of equation in higher orders, right?
Yeah, so we have part of that, but we also have the part that's not that. That's actually I would label as quantum. Why wouldn't you label it as quantum?
No. There's the other part, which is a real quantum integration, is not included in this way. So it's the part which you called H, whatever, or another part. It's still not iteration in external current.
So you're saying that this is not a quantum correction?
Yeah. Yes. No. This is the last one. I'm not sure if it's probably this quantum correction, because this is not given by iteration of external.
Yes, that's what I mean. So the words, your iteration external current, I completely agree.
Yeah.
And that's what I've labeled as classical.
No.
But there's also this quantum piece, right?
No, there is quantum piece, but the one you are calculating, it is still classical.
At the end, for the binary piece.
Yeah.
Yes, absolutely. We don't carry around the quantum piece because A, it's so small, and B, it would be so hard to do the calculation.
This quantum piece you are talking about it is about long range. There is another quantum piece which is not of long range and which is not calculable.
Yes, agree. Yeah.
Okay, that's it.
Yeah, I don't see any other, oh, one more question.
Can you say a few more words about how the identification is made between gravity and Yang-Mills squared? A bit more precisely.
So yeah, I didn't write out the mathematical formula, but so again, this is there are these functions we call amplitudes to describe this process. If you write out that amplitude, you can literally see as a mathematical formula that it contains two factors of that for the Yang-Mills inside gravity. There are factors in front, but morally we call that the double copy. So I'm literally talking about a function B that you can write as A of X, A of Y, and these A function is the one that describes the one for Yang-Mills.
Okay, and how do you fix the prefactors? There's some matching that has to be done, or?
How do you fix? Oh,
Yeah.
what?
Yeah, you said there it's the squared up to prefactors.
Oh, I just mean that it's not exactly just two copies of A. There's also some prefactor there, but the prefactor you can just see in the equation. It's not. Yeah.
This must be a very basic question, but can you say in this framework, all these ancient issues that people, Abraham, Lorentz, Dirac et al. Faced in dealing with radiation reaction, these third order equations, all this funny business. Presumably it's all solved quantum mechanically, but can you say where does that show up? Does that show up in this formalism? And where does it show up? I asked because you said the word self-force, but
Yeah.
I thought there'd be some discussion about Dirac and
Yeah.
third order.
Right. So the same issues show up in the sense, I mean, in fact, the whole business of self-force is trying to, for example, regulate the force of this particle in itself and defining the fields appropriately. Where exactly it shows up in the self-force calculation.
Before getting to self-force, there's a linear divergence in the energy in the electric field that's solved by positrons, antiparticles and so on, softened to a log. So even before getting to radiation reaction, quantum mechanics is coming to the rescue. I'm just wondering if is there something like that here as well? Maybe the fact that it's gravity means that you don't see it because G Newton is dimensionful.
I thought there should be similar divergences. And I don't know how they deal with it in the self-force formalism. They definitely have to regularize the fields. In this framework, so in this framework, I can tell you that essentially what happens is that you're essentially calculating basically a self-force of a particle in the background. Because like I said, what you consider are the sum of these graphs where the bottom guy has one propagator and the top guy has as many as you can have. And the top guy basically resums to the background. And so essentially, if you view the top guy as the background, then you basically are computing insertions of the background. And here in the second line here, you're basically have a self-energy loop with one insertion of the background, two insertions of the background, and so on and so forth. So that self-energy loop has to be regulated. And yeah. But I guess the divergence, so I guess at higher order, you need to add a counter term to regulate it, just like a self-energy graph. I mean, these diagrams in flat space also get divergences at higher loop. So The divergence for 2-2 scattering at higher loop, which you would need to regulate with a counter term, should also appear here, but should appear as a self-energy graph. That's how I would imagine it appearing here. Yeah, I wish I could tell you how they exactly regulate in the self-force approach. If I remember correctly from discussions with them, I think they definitely do, but I don't know the details of how they deal with that. Self-force.
And strange runaway solutions and so on. Anyway, sorry, I won't keep going on, but presumably the people doing the classical calculations have some way of dealing with this problem at this ridiculously high order, so.
Yeah, like
Okay, well, let's thank Mikhail again for a great talk. And so it's break time, then we start again at 3:20.
you never do anything.